And then the first part here. So what are compression members? So we discussed it. Some examples. Where do we see them? Okay. What are the limit states like general buckling and local buckling as well? So we differentiate the two. So general buckling is the instability of the member itself, while local buckling is the instability of the components. Uh, so there's the illustration showing the difference between the two. And then we also discussed the Euler buckling theory. So we discussed the types of general buckling that we may encounter. Okay. And we discussed Euler buckling theory, which serves as the basis in explaining or describing the flexural buckling behavior of columns. Okay, so there you go, the assumptions, the formula for the critical buckling load. Okay, so we also discuss about the effective length factors, which depend on the support conditions. Okay, we also discuss the slenderness ratio, the parameter KL over R, and the its importance in expecting or expecting the behavior of a given column. So we know last time that the higher the slenderness ratio, the higher the susceptibility of the said column to buckling. Okay. So we also discussed the effect of bracing. So it changes the effective length of the column. We also discuss an example as well how to determine the critical slenderness ratio. So there you have it. So do you have any questions with our with our last lecture, last Wednesday? Any questions so far? I guess wala. Okay, so with that, let us go with the next topic, inelastic buckling. So we have the assumptions for Euler buckling theory. So for example, the material is elastic, the axial load is applied at the centroid, the member is perfectly straight and prismatic, all of those assumptions. No? However, uh, not all of those assumptions are always fulfilled or satisfied, more especially in structural steel columns. Another thing that we can highlight is it is observed that assumptions laid out for Euler buckling theory are not always completely satisfied in all cases. Furthermore, uh, the test results of actual columns, actually see here. So this is a buckling load. So yun yung y-axis against the slenderness ratio. Okay, so so ito yung graph na to. So the x-axis is the slenderness ratio, y-axis is the critical load. This is the supposed formula for the Euler buckling load. Okay. So for higher slenderness ratios, you can see that the range where test results are located pretty much follows the Euler buckling curve. So this one, ito yung curve na that you can plot, okay, with this formula. So at higher slenderness ratios, it roughly follows this trend set by the Euler theory. However, for columns with lower slenderness ratios, what happens is that it does not follow the Euler buckling curve at all. So the test results are actually, the resulting test results are actually lower than what you expect if you use the Euler buckling formula. Okay. So what are the reasons? No? why do we have test results that do not always trace this curve by the Euler buckling formula? So, so some of the reasons are this. So we have the residual stresses. So what do we? So residual stresses are initial stresses that occur in structural steel members due to the following. So first, uneven cooling after the hot rolling process. So after you manufacture your structural steel members by hot rolling, what happens is that you usually cool it down by air, and what follows is that the ones that cool down first are those that are at the outer surface of the member, and then the inner surface remain hot. Okay, and that causes thermal stresses on our structural steel member. So ibig sabihin, may initial stress ka na. So konti na lang yung load na i-apply mo bago siya say mag-fail. Okay, so that's one cause. Next, cold bending during fabrication. So for example, you want a curved beam. Nakakurba yung beam na gusto mo. So you need to bend that curve, that member para ma-satisfy yung requirement mo, right? So you do cold bending. When we say cold bending, you bend the members without applying heat. Okay, so pretty much parang yung sa rebar fabrication process na. Pag gumagawa kasi ng stirrups or ng main bars and you need to bend, no? It's similar, no? So it's similar in case that in the case na hindi ka nag-apply ng heat. You just bend it by force, no? So that's cold bending. So if you bend a member, meaning you apply force, right? So meaning you apply stress on the member. So that stress is also counted as residual stress. Okay? Third, we have punching of holes and cutting operations during fabrication. So you apply shear stress as well. No? So meaning there is residual stress. Okay? And lastly, welding. So welding meaning you apply heat. So the mechanism is pretty much similar to this, to uneven cooling, no? In the case that the initial stresses are caused by heat. Okay? So these are some of the causes of residual stresses. So what's the effect of residual stress? It lowers or decreases the capacity of the member to carry the required loads kasi may initial stress ka na. Okay? So that's one of the reasons behind this test results. Okay? Another reason is that the axial compressive load is not always expected to be applied through the cross-section. So meaning, nagkakaroon ng eccentricity. Okay? So kung nagkakaroon ng eccentricity, you develop additional bending moments on the member. Okay? And if you have additional moments, you introduce additional stresses. Okay? So that's why bumababa yung load na kailangan mong i-apply, no? Para mag-buckle siya or mag-fail. Third is distortion of the cross-section due to local buckling. So we will discuss more about local buckling, no? Although you are already familiar with this, no? So instability of the component, the web. So we will discuss about this later. And other factors such as the end restraints or supports. So yung supports, they are not always perfect. Hindi porket inassume mo siya na fix, palagi siyang fix. Okay? So next, we have straightness of the member. So for example, meron siyang may konti siyang camber, no? Or may konti na siyang deflection before you erect the member. Or medyo tabingi siya, no? So it affects yung application ng load mo. Right? So there are your reasons why the test results here do not always comply with the Euler buckling curve. Okay, so in this case, this contribute to the occurrence of the phenomenon known as inelastic buckling. So, lahat ng to nagko-cause ng tinatawag na inelastic buckling. So, especially for columns with small slenderness ratios, inelastic buckling yung go-govern na buckling mode. Unlike for longer columns, we are long columns with the higher slenderness ratios, slender columns natin. Okay? So, ang nag-govern dito is yung Euler buckling or elastic buckling. Okay? So, some theories on inelastic buckling were developed. No? So, considering all of these factors, no? So, such as the basic tangent modulus theory by Engesser and the inelastic column theory by Shanley. However, we will not go into these theories in detail. So, the important thing here is you are familiar that there are such theories. No? And these theories explain and form the basis for our code provisions. So yung mga formulas natin na nasa code for the design of compression members, the rationale behind those are these theories. No? So there you have it. Okay. So for more information on Euler buckling theory and inelastic buckling, you may watch this video. So I will just play the first part of this, the first 20 minutes or so. Okay. But the rest, lahat ng nandito, in-explain nila how it affects yung column capacity natin. Okay. So I will just play the first 20 minutes. May konting introduction to since this video comes from a webinar by AASC. So just bear with it. No? So the important thing here is it will explain yung Euler buckling theory. Okay. Yung other parts like yung inelastic buckling, although nandito sa video, we will not play it. No? So I will leave it up to you para panoorin siya. Okay? So let me play this one. So do you have any questions so far with our with what we are discussing? May questions? Okay, none so far. So let me just play yung video natin. So
Hello,
just
everyone,
ping me
and
in the
welcome to.
chat box no kung may problem sa video or sa audio. So if you see the video is 1 hour 30 minutes pero I will not waste our time watching the entirety of the video. So I will just go at somehow around the 22 or 23 minutes na of the video. So there you go. Okay? So again, pag may problem with video or audio, please put it in the chat box para ma-check po. Okay? Okay, so let's start.
AISC's Night School Fundamentals of Stability for Steel Design. This is presented by members of the Structural Stability Research Council, and today is Session 1, Course Introduction and Behavior of Compression Members. My name is Patrick Newman, and I'm with the AISC Continuing Education Group, and I'll be moderating today's presentation. I would like to introduce today's speaker. Ron Zimian is a professor of civil and environmental engineering at Bucknell University. In addition to authoring papers on the design and analysis of steel and aluminum structures, Ron is co-author of the textbook Matrix Structural Analysis and the editor of the 6th edition of the Guide to Stability Design Criteria for Metal Structures. He is currently chair of the Structural Stability Research Council, as well as AISC's Task Committee 10 on Frame Stability. He recently completed his term as chair of AISC's Task Group on Inelastic Analysis and Design. He serves on the AISC and the Aluminum Association Specification Committees and is active with the Steel Joist Institute. In 1994, Ron was awarded the ASCE Norman Medal, and in 2006, he received AISC's Special Achievement Award. Last month, Ron received the ASCE Short Ridge Hardesty Award for his substantial accomplishments in research, service, and teaching, as well as advancing practice in the field of structural stability. And with that, I'd like to turn it over to you, Ron.
Well, thank you very much, Patrick. It's my pleasure to be participating this evening. Just change slides here. First, I should mention that the Structural Stability Research Council is very pleased to be joining AISC and delivering one of their night school courses. As the title of the course indicates, over the next several weeks we will be focusing on the basics, the fundamentals. So really nothing super sophisticated, but simply those topics that one might consider essential to the stability of steel structures. A little bit about the course. The session topics include 2 lectures on compression members, 2 on flexural members, 2 on systems and beam columns, and then the last 2 will be on bracing. Each one of these session topics is presented in 2 parts. The first part, for example, tonight's lecture, will focus on the behavior in the background, and then the following lecture on that topic will focus on the design issues. So our lectures are all being given by members of the Structural Stability Research Council, and they include Perry Green, Todd Helwig, Don White, Joe Yura, and myself. And again, it's great to be joining AISC with this effort. As I said, the focus of the course is on fundamentals, and I think the first thing we should do, or I'd like to do, is just provide some working definitions. So I've got 3 terms here that I think are important and that really need to get us up and running. You'll notice that I'm not even going to try to attempt to define the word buckling. That has so many different definitions, and it's just been used so broadly that I think we'll just focus on 2 other concepts here. But first, in general stability, what that basically would mean to me, and hopefully to you, is that if a system or a component is under load and you were to provide some type of a small disturbance to it, upon removing that disturbance, the structure would return to the state it was before, still under that load. So it wouldn't fall over, tip over, or collapse or anything like that. So that's in general stability. Now when we go into the worlds of buckling, there's basically 2. The first we might call bifurcation or critical load. This is more of a theoretical thing. It's really a theoretical point in which loading a component results in an instantaneous change from its current state to a significant amount of deflection. So those are big words. What's that all mean? The bifurcation is simply a theoretical point where you go from it's not buckled to it is buckled. All right? Instability, on the other hand, this is a much more realistic transition in which as you're loading a component, you're getting small deflections at first, and then all of a sudden you start getting some pretty significant deflections. And then finally you're sort of declaring the structure as unstable. So this would be sort of buckling preceded by significant amount of deflection. So tonight we're going to be looking at different possibilities here. We'll be in the bifurcation world for a while, and then we'll be spending a lot of time in the instability world. Some background on structural steel and how we get to all these stability issues. The first thing is that structural steel really has excellent strength to weight ratio and an excellent stiffness to weight ratio. And because of these awesome factors about structural steel, you end up using a lot less when you start thinking of economy in amount of construction materials. And as a result of being able to use less, your components end up to be very slender or skinny. Now, this inherent slenderness results in almost all strength limit states needing to consider some form of an instability. So like we said, we're going to look at course lectures, trying to understand the behavior, compression members, flexural systems, and then we'll finally wrap up with looking at bracing in order to increase the capacity of these members. So let's move into, so that was just a brief introduction of where this course is going and a couple of definitions. Tonight I'm going to focus on the behavior of compression members. Limit states of compression members. So we've got a bunch of different ones. The first one we could call full yielding. So we'll touch on that basically. And then instability. So it could be along the member length, and it could come in the form of flexural buckling, torsional buckling, or flexural torsional buckling. Or it could be at the cross section in the form of local buckling. And so tonight we're really going to look and focus on this flexural buckling aspect. But before going there, let's have a look at the full yielding. So let's go all the way back to the beginning when we, were performing tensile tests, or if we took a piece of structural steel, put it in a testing machine and stretched it, and we monitored its stress and strain properties. And what we would see is basically on the screen here, we'd start off with no load, and as we applied load, we'd get a nice linear response. And at some point, I'm going to track the blue curve here, we'd get some yielding, we'd have a yield plateau, then some strain hardening. Eventually, we'd reach the ultimate, and then we would rupture the material. Now, this diagram is not to scale at all. Steel has some amazing ductile properties. And in fact, I tell my students that if they were to put their nose on the 0-yard line and reach out 1 yard to their right, this would be this point. And then if you were to look down at the 10-yard line of the end zone that you're at, that would be that point. And then if you could see the far end zone, that would be that point. So there's a lot of ductility going on with structural steel. Now, what we're going to do is assume that the material is elastic and perfectly plastic. So it either has its full modulus elasticity or the E value is 0. So we're going to be neglecting then the strain hardening. One of the things that we'll be doing this evening, because everything is in compression, is we'll be assuming that the yield strength for compression is the same as the yield strength for tension. And both of these then will be the yield value. And like I said, we'll also be neglecting the strain hardening, so we'll be assuming elastic, perfectly plastic material. So if we just think about the full yielding aspect, we could come up with our first column curve. And so over on the right here, I have a column we're testing. And what I'd like to do is plot the strength of the column versus its length. So on the horizontal axis, I have its length. And on the vertical axis, I have its strength. And if all we were to consider was yielding, what we would have here is a column that would always be able to reach its full yield capacity. So the question is this zone then in which you might be in, is it acceptable? And I think you're aware that for probably very short, stocky columns, we could reach the full yield. But the second the column has any significant amount of length, there exists the possibility of buckling, so some type of an instability. So I would say that this criteria, this column curve, would be unacceptable. And so what are the possibilities then? Well, we could have a member type of instability or a cross-section instability such as local buckling. And like I said, we're going to focus on the member instability part. So what are the possibilities of a member instability? Well, we could have flexural buckling like I'm showing on the right here. So here's a large test going on, I believe, at Bechtel. I'm sorry, at Bethlehem Steel, an older photograph. And it actually may be a test being taken place at Lehigh now that I look at it more closely. But nevertheless, we've got a column in a giant machine being squished, and you can see that the column is flexing or bending, and as it's reaching its buckling capacity. On the other hand, if you were to take a cruciform section and subject it to axial force, the failure mode would be very different, no flexing or bending, but much more one of twisting. So that would qualify as torsional buckling. Now, if you move away from a shape like I'm showing down here at the bottom, these bisymmetrical shapes, I shapes or HSS shapes or back-to-back channels, in which the centroid is in the same spot as the shear center. And again, the shear center is the spot that if this was a beam and you were to load it, it's the point where you could load without any twist occurring in the beam. The beam would just bend. So for cases like I'm showing over on the right here, a T section or this channel, where the centroid and the shear center are not at the same location. So for the channel, for example, the centroid is it's where the x and y axes intersect, and the shear center would be out here someplace. If you subject these to compression, you're not going to get just flexural buckling. You'll get twisting as well. So we tend to call this flexural torsional buckling. So those are the ones, and like I said, tonight we're going to focus on this flexural buckling case. So flexural buckling. Well, what we're going to do is we're going to start having a strong look at Euler's column, his solution, and the assumptions he made. And then we're going to try to approach reality by undoing each one of those assumptions and what's involved with undoing the assumptions. And then I'll end up looking at column curves, one, what's in the AIC specification, and then what some others are doing elsewhere in the world. So Euler buckling. All right. I'm going to get my notes together here. Euler was a Swiss mathematician and physicist, and 270 years ago, he was out solving some math problems and stumbled across a structures problem in which he solved using differential equations. So this was in 1744. Over on the right was the publication in which this concept first appeared in. 1757, that's 13 years later, and that's when the AIC specification adopted Euler buckling. Okay. All right, that was a joke, but because we're on a webinar, I can't hear all the laughter. Obviously, there was no AIC. There was no A, as in America at the time either. So this was a long time ago. But anyway, Euler buckling. Some assumptions. Euler assumed that the member was prismatic, so it had a constant I along its length. We had small deflections just at buckling. We had no bending prior to bifurcation. So Euler is going to talk about buckling. So the column, as I'm showing down on the right here, is either perfectly straight with load on it, or 1 instant later, it's buckled into this flexural shape that I'm showing on the right. So no bending, which means it has to be perfectly straight, and that load has to be right through its centroid. We're going to assume, Euler is going to assume linear elastic behavior, so the E will be constant, and the support conditions are going to be pinned roller. So what is Euler going to do here? Well, what we basically do is we start just after the column buckles, and only a small amount of buckling, a small amount of deformation, but we have reached the Euler buckling load. So what I'd like to do is draw a free body diagram. So I'm going to make a cut here, and here is the upper portion of that structural member. We've got the axial force, the Euler buckling load on it. The member is flexing, and the deflected shape is being described by this function v of x. And to have equilibrium down at the bottom here at my cut, which is x away, we have an axial force acting upward and a moment in the column. So we've got two things we can work off of. First, just equilibrium. If we sum moments about the base here, so here's the base, a star, and I sum the moments, well, what have I got here? I've got the moment, okay, m of x, and I also have this Euler force acting through a moment arm, v of x, also contributing to that moment equation. So those are the two components of moment. I add them together, and if the thing is just in equilibrium, it should equal 0. Now this moment term here, m of x, is related to the deflected shape, v of x, and that's our moment curvature relationship. So I'm sure all of you know this moment curvature relationship. You've been using it in moment area, conjugate beam, whatever method is your favorite method for calculating deflections, and it's basically that the internal moment in the beam is equal to EI of the beam times the second derivative of the function that describes the deflected shape. All right, so what we're going to do next then is we're going to make a substitution, and we're going to substitute this term in for m of x. So when I do that, I'm down at the base here, over on the left, what I end up with is a differential equation. All right, so don't go running out of the room yet. Stay here. It's not over. You can solve a differential equation. No, you can't. All right, if you can't solve a differential equation, Well, most of our students can either today, and what they've been all relying on is their new calculators, which have symbolic processors in them. And so it seems that they just smile when you tell them, all right, you got to solve the differential equations, where years ago we used to just cringe. But I do reference you to some fun software at this website here, where you can just type in the differential equation, hit go, and it will give you the solution. But anyway, we've got this second order differential equation, and voila, over on the right here, I've solved it. And what it's basically telling me is the function just at buckling, v of x, is equal to a constant times a cosine plus a constant times the sine. So in our quest to find out what those constants are, what we're going to do is have a look at the boundary conditions. So I had described this point as my origin. So at x equals 0, we should have no lateral displacement. So v at x equals 0 should be 0. So if I come up to this equation and I plug in 0, the sine of 0 is going to be 0. The cosine of 0 is going to be 1. So v at x equals 0 is c1, and c1 needs to equal 0 for that boundary condition to be satisfied. So what that basically means is that this term is not in the equation at all. It's also telling us that the buckled shape is a sine wave. All right. So let's use our second boundary condition then to see what information we can get from that. So we've got the fact that the curve is a sine wave. And in our quest to find out what C2 is, we say, all right, well, v at the far end at x equals L, the lateral displacement also has to be 0. So we got 0 is equal to C2 times the sine of that portion there. And again, we're computing this at x equals L. Now, we've got two solutions. The first is what the mathematicians call the trivial solution, and we could just call C2 0. The problem is if we call C2 0, then v of x is 0, which means basically the column never buckled. But we're looking for the buckling solution. So we're going to ignore that trivial solution, and we're going to go to the second possibility, and that's that this sine term right here, over this portion here, must equal 0. So if we take that and we realize that sine takes on a value 0 at n pi, where n is 1, 2, 3, or 4, 5, 6, 7, 8, whatever you've got. So we've got in this portion here, it needs to equal n pi, square root of p, or the Euler buckling load divided by EI times L must equal n pi. We can solve then for the Euler buckling load, and it's n squared pi squared EI over L squared, where n takes on the values 1, 2, 3, etc. Now, as I indicated earlier, Euler is solving for the bifurcation load. So what that means is if we take our column, so here's the column, and we're loading it up with our axial force, if we were to monitor the lateral displacement, we would have none, no lateral displacement, no lateral displacement, no lateral displacement, until suddenly we hit the Euler buckling load, and then we would have bifurcation and the deflection would become unbounded. So that's what we're saying. Now, the second thing is you can see that it's difficult, well, impossible, for us to get above the first buckling mode. Because if we want to get up to the second buckling mode, where n equals 2, for example, and the buckling load is 4 pi squared E over L squared, again, that n is squared, as you can see in the upper right, that's 4 times as much load. Well, to get to, let's say, 4,000 kips, I would have to go through 1,000 kips first. And when I went through 1,000 kips, the column would buckle. And likewise, theoretically, we could find the third buckling mode, n equals 3, n squared is 9, and we could have 9 pi squared E over L squared. But the bottom line here is that the first mode is going to control. But you might ask, well, is there any interest in these higher modes? And the truth is, yeah. If we start thinking about where to brace the column, these higher modes might tell us, this, for example, might be a good point to brace it. So if we start thinking about optimal location of bracing, and those higher modes could be very useful. So, okay, so we've made a big step here. We've now got the Euler buckling stress. And how we get that is we take the Euler buckling load, pi squared EI over L squared. So this capital E down here, that's capital E for Euler. So the Euler buckling load is pi squared EI over L squared. And if we divide by the cross-sectional area of the column, and we introduce the radius of gyration as the square root of the moment of inertia divided by the area, we end up with an expression that says that the Euler buckling stress for the member is pi squared E divided by L over R quantity squared. So we've now been able to take into effect the fact that the member may buckle. So we've got a second chance now at a column curve. We'll take the information we knew before, and that was we could never get above the full yield, sigma y. But also on this, now we can include the Euler buckling stress. And you can see what happens here is the column gets long and slender. So now I'm plotting L over R, the slenderness on the horizontal axis. As it gets longer, the Euler buckling stress gets much, much smaller. So it's easy to buckle a column that's long and slender. Now, an interesting thing happens is when the column, say, gets below in this slenderness range, we might try to get to the Euler buckling load, but we can't get to it until we fully yield the column. So we've got now our second take at a column curve that says anything that's in this green area here below full yield and below the Euler buckling stress should be acceptable. And life would be great, except for Euler had made several assumptions. So we need to go back and have a look at those assumptions.
Ron, can I interrupt for
sure.
a second here?
Yeah.
I got a question, and it's going back on slide 13.
Alright, so there you go, no? So yung you only just highlighted yung types of buckling that may occur, and at the same time yung Euler buckling theory. Okay, so let me just go back to some of the points here. Ito, no? So some of these definitions. So when we say bifurcation dito, no? Yun yung load kung saan if you apply it, 'di ba, for example, straight yung column mo. If you apply that load, it suddenly deflects. Okay? So it suddenly deflects. So ang tawag natin doon sa load na 'yon na nagko-cause ng ganung behavior is what we call the bifurcation point. Okay? So that's one thing. Another thing dito sa stress strain diagram natin, the actual stress strain diagram of steel, we can trace it dito. Right? The blue one or violet one, whatever colors this, no? So, however, we do not consider itong part na kung saan tumataas yung stress mo beyond the yield stress. So, ang ina-assume natin, once it goes past the yield point, magiging plastic na siya. So, hindi na siya magkikerry ng additional stress. Okay? So, we call this the idealized elastoplastic material. Okay? So, yan lang yung ina-explain niya dito kanina. Okay? And then there you go, no, yung types of buckling na pwedeng mag-occur. So, you have yung flexural buckling, yung torsional buckling, and flexural torsional buckling. Okay? And then the rest, it's just yung derivation ng Euler buckling theory. Okay, so kumuha lang siya ng FBD dito. Ito yung deflection ng curve mo. Deflection ng column mo. And then he just made a free body diagram. Ito yung in-apply mo. And then ito yung internal loading at this point. No? So dito siya nanggaling yung ano natin, no? Yung Euler buckling load. Then dito, in-explain niya lang rin yung buckling modes na pwede mag-occur. Okay? So usually ang kino-consider lang natin is yung fundamental buckling mode, yung first mode, because in order to na pwede mag-occur yung second or third mode, you need to apply more load. Yun yung in-explain niya dito para magkaroon ng ganitong buckling curve. Okay? But the critical is the most critical para sa atin. Ito yung may pinakamababang critical load. Okay. So kailan mag-occur itong higher modes natin? Kapag meron tayong bracings. Okay. Because kapag may bracing ka, you force it to buckle on a certain mode. So for example, brace ka dito sa mid, hindi mag-occur itong first mode kasi naka-brace ka dito. Right? So ibig sabihin, to uh, it has to uh, apply more load para lang mag-buckle. And ang magiging buckling shape niya is kapag yung isang unbraced segment ay magbabuckle ng buo. So it would buckle this way and yung other segment, it would buckle the other way. Okay? So kapag may bracing ka, that's the time that you will be able to attain yung higher modes natin. Okay? So there you go. May questions about the video? Questions? Okay, sige. So mukhang wala. Okay. So let me go back with with our screen. So nakikita nyo? Nakikita nyo na yung screen? Okay. So this time we will now be explaining the other expected limit state for compression members, no? And that's local buckling. Okay. So again, no, we explained that local buckling occurs when the section components itself becomes unstable due to applied loads. So yung flanges or yung webs yung nagbabakal instead of the member itself. Okay? So if yung sa column itself, meron tayong slenderness ratio, yung mga flanges tsaka yung webs natin, they also have their own slenderness ratio. Okay? They have a similar parameter. We call this the width thickness. Okay? So the width thickness ratio of so the notation for this is a lambda. For flange, we call it lambda F. For web, yeah, we call it lambda W. So before we proceed with how do we actually determine yung width thickness ratio, okay? So let us first discuss the elements on a structural steel sections. So structural steel sections are composed of either stiffened elements, or both. So when we say unstiffened elements, these are section components that are supported along one edge parallel to the direction of loading and unsupported on the other. So if we take a look at the example here, a flange is an example of an unstiffened element because dito sa edge na to, no, supported siya, pero sa kabilang edge here, hindi siya supported. Right? So we call this an unstiffened element. Okay? When we say stiffened, it is supported on both edges. In the case of a nice section, the web, so that's differentiate the two elements. Okay, so important because the presence of unstiffened elements actually increase the susceptibility of the section to local buckling. So may mga other sections that are not really, although we check for local buckling, pero they are less likely to be susceptible to the limit state, like say yung mga HSS natin. Okay, though so yung HSS sections natin na yung mga hollow structural steel sections, uh, all elements are stiffened. Okay, unlike yung mga angles, wala siyang stiffened, puro unstiffened. Channels, dalawa yung unstiffened, yung dalawang flange, tapos yung web niya is stiffened as well. T-sections, walang stiffened, lahat unstiffened, no? So, there you go. Okay? So, then, structural steel sections, components subjected to axial compression are classified into two in terms of local stability. So, meron tayong tinatawag na compact or slender components. So, when we say compact, these are section components that are not susceptible to local buckling. While slender, these are susceptible to local buckling. Okay? So, paano natin malalaman yung compact, kung compact yung component natin or not? So, we actually compare yung width thickness ratio. So, for the flange, the width thickness ratio is B over T. Yung B is half of the flange width. If you see yung diagram natin, over yung thickness ng flange. For webs, we have H over TW. Yung H dito, sa ASEP handbook is yung capital T na variable. Okay? Capital T. So, kasi iba siya dun sa, so if you pag-measure niya ng capital T dito, hindi siya nakasagad sa surface ng flange. Kasi meron tayong parang some sort of a corner here. No? Pero hindi siya yung kantuhan na right angle, kung mapapansin nyo. No? Kung nakakita na kayo ng actual na steel section, no? Usually medyo pabilog to. So we call that a fillet, yung curve na yon. And yung dulo ng fillet yung ginagawa nating reference for the measurement of this dimension. So yun yung capital T. Okay? And then yung TW is the thickness of the web. So ito yung mga width thickness ratio. Okay? And then ito yung mga so ito valid lang to for yung formulas natin dito is only valid for I sections, okay? Kasi yung dinidiscuss natin sa module na to, puro I sections lang yung gagamitin natin na hot roll. Okay? So ito yung mga limiting values. Kapag ito nag-less than, pag yung actual width thickness ratio mo is less than or equal to this limit, so for example sa flange, ito yung checking mo. Kinuha mo yung actual width thickness ratio, you compare it to this limiting value. Pag nag-less than, ibig sabihin, hindi siya susceptible to local buckling. So we call that flange a compact flange. So compact yung flange, ibig sabihin. Pag nag-greater than siya dito, slender siya. Okay? So that's how you determine if a component is compact or not. Same thing with the web, ganun din yung concept, pero iba lang yung criterion natin. So iba yung pag-measure ng width thickness ratio mo. So as you see here, ito yung limiting value. Pag nag-less than dito, it's compact. Otherwise, slender. Okay? Then, structural steel sections which have all of its components classified as compact are called compact sections. So for example, compact yung flange upon checking and compact yung web. Ibig sabihin, the entire section is compact. So meaning, it is not really much susceptible to local buckling. Yun lang ibig sabihin nun. Otherwise, pag may nag-slender dito, kahit isa lang sa kanila, we call it a slender section because merong part ng section na critical for local buckling. Okay? So, the good thing, tape sections are considered to be compact. Most, okay? Not all. Pero for this class, you still need to do yung stability check. So this one, itong formula dito. Okay? So you still need to uh, to check yung local stability ng section mo, whether compact siya or not. Kahit na alam natin na most of the I sections na hot rolled ay compact. Okay? So now, where do we actually see this formula right here? So we see it in section 502.4 ng 2015 NSCP Volume 1. So nandito ina-explain niya yung local stability check. Okay? And then may dalawang tables doon, tables 502.4.1 and 502.4.2. Okay? So again, yung section lang na gagamitin natin is hot rolled I-shaped sections. So considering yung section na gagamitin, they are in axial compression, and upon checking the table, for flanges, you use their case 3. Case 3 ng table na to. For webs, case 10 should be used. Okay? And then, yung nandito na limiting values ito yung lambda R, or yung limiting value for compact components. Okay? So, there you have it. No? So, any questions so far? Do we have some questions? Okay, so wala. So before we proceed with the example, no, so let's watch a video related to local backlink. So ito. So you don't have to worry about audio. Walang audio to. Okay, so it just explains no yung mga diniscuss ko kanina. Okay? Okay, so there you go. Okay, so kung nakikita nyo dito, you can say that every steel section that we have can be divided into several plates. So in the case of the I section, you can actually divide that section into 3 plates. Yung dalawang flanges tsaka yung isang web. Okay? So let me go back dun sa sa graph. May non-compact dito, but this non-compact is only applicable for beams. Dito yung limit natin. So lahat ng nandito, we consider them to be compact up to yung lambda R. Beyond this, we call it yung slender. So yun yung for compression members. For beams, talagang tatlo yung division natin. No? So we will explain that next time. Okay? So there you go, no? So it just explains the mechanism of local buckling and how it affects yung members natin. Okay? So let's go back with the module. So now we explain how do we actually use this criteria to check if the components of the certain section I section are compact. Okay. So we have this check the compactness of the following sections under actual compressions of W14 by 730. So ito yung properties niya. And then we also have W18 by 311. So for both cases, under axial compression, parehong hot rolled I shape. We use case 3 and case 10 respectively for flanges and webs. So we first have W14 by 730 made of A36 hot rolled. So this time hindi muna ako gumamit ng ano no ng asset handbook. Just to demonstrate yung use of the CSI steel. So I just select the section and then there you go yung dimensions niya. This one. So the compactness of flange, I check it. So lambda of the flange is half of the flange width over TF. That's why BF over 2 yun nandito. All over TF. Okay. And then you just substitute this. Makakuha natin yung width thickness ratio to be 1.823. This one is the limiting value for the flange, for the compactness of the flange. So it is important that if you sa parameters right here, the units must be consistent para mag-cancel out because the width thickness ratio is unitless. So kapag nag-SI ka, SI lang. Pag nag-English ka, English lang. Pareho din naman yung lalabas ng sagot dito. So yung etong formulas applicable for both SI and English, no? So yun yung kagandahan ng mga formulas natin sa steel. It is applicable whether the system of units is SI or English. Unlike sa RCD, mag-iba ka lang ng units, mag-iiba na yung mga formulas mo. Okay? For steel, we do not have a problem with that. As long as your units are consistent, it's alright. Okay? So there you go, you just substitute it and then you compare it. Yung actual width thickness ratio is less than the limiting width thickness ratio. So therefore, the flanges are compact. So just like what we have here in this criteria. So this first one is for the flanges. Itong pangalawa is for the webs. So we also need to check yung compactness ng web. So dito, is supposed to be yung capital T sa asset handbook. Kaya lang, the problem here is we do not have the dimension dito sa CSI steel. So kung halimbawa, wala kang handbook, hindi mo makakita yung dimension na T, na capital T, how do you approximate yung dimension na to? Okay? So ang ginawa ko is, you have the depth of the section, i-minus ko lang yung dalawang flange thickness. So makakuha ko tong dimension na to. Tama ba? So I can use that for this. That's why ganito yung ginawa ko. Okay? Pero kung may asset handbook kayo, we just use yung capital T na value. Yun lang ang substitute na dito. No need to add or subtract anything. Yun ay kung may handbook ka. Pero pag wala, you may use this one. Okay? So, and then you just substitute it, you operate it. Ito yung lalabas. Then, here's the limiting value. Ito yung lalabas. Again, itong actual is nag-less than sa limiting value. So, therefore, the web is compact. Okay? And since the flat are compact, therefore, is considered to be compact. So that's how you check yung compactness of an I section. Okay? So for letter B, similar lang yung calculation, no? Nag-iba lang yung section tsaka yung material properties na. So direction check. So okay. Disclaimer note here na may mga konting difference in dimension sa ASEP handbook tsaka sa CSI still. No? But apart from that, pero konti lang, minimal lang naman yung differences na. So okay lang rin. Kung wala kayong handbook, you may use CSI still for this. Okay? So there you go. So that's how you perform yung local backlink check, yung compactness ng I section natin. Any questions? Questions? I guess, paano po yung isa nag-non-compact or nag-slender? Eh di hindi na compact yung buong section. Slender na siya. Okay? So, para maging compact yung isang section, dapat lahat ng components niya compact. Okay na? Okay. Any other questions? I guess wala. No? So, let me now, so we are now good with the local backlink. So, let us now proceed